Hello, Algebra students, and welcome to another lesson. We are in section 7-5, day 2, and we are simplifying radical expressions. What I'd like for you to be able to do is to define what a radical is and write radical expressions in simplified form. So in order to simplify radical expressions with square roots, you must know the perfect squares. Perfect squares are numbers that, when taken the square root, give a whole number back. So for example, let's just take some of our numbers and square them. So these are perfect squares. So if I take 1 times 1, that equals 1. 2 times 2 equals 4. 3 times 3 equals 9. So 4 squared means 4 times 4, which is 16. 5 squared means 5 times 5, which is 25. 6 squared is going to give us 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and x squared is just, it means x times x, but if I don't have a value for that x, then it's still just x squared. So notice when I have two numbers getting multiplied by themselves, I'm getting these perfect squares. I can take that in reverse to do square roots, which is what we started talking about yesterday. So the square root of 1 is 1. The square root of 4 is 2, because 2 times 2 gets you 4. The square root of 9 is 3. What should go in the square root to get 4? That's going to be 16. Now, if we are to keep following this pattern, what is going to need to be inside the radical to get a 5? Well, that's going to be 25, because the square root of 25 is 5. The square root of 36 is 6. The square root of what gets me 7? Well, that's going to be 49. And the square root of 64 gets you 8, while the square root of 81 gets you 9. So what multiplied by itself gets me x squared? Well, that is x, because x times x gets me x squared. So notice how these two columns relate. They are inverses of each other. They are the exact opposite. So let's practice that with some perfect squares. So we are going to simplify some square roots. It's okay that we have more than one type of thing inside of our radical. If we want, we can separate this out. So this means the square root of 9 times the square root of x squared. And that might be easier for us to handle. What is the square root of 9? If you need to go up to your table, then you can, but we're going to be memorizing these because we use them so often. So the square root of 9 is 3, and the square root of x squared is x, and that's my answer. If I need to, then I can separate this out as well. So what is the square root of 64 times the square root of x squared? Well, the square root of 64 is going to be 8, and the square root of x squared is x. Let's separate this one out. The square root of 49 times the square root of y to the 4th. What multiplied by itself gets me 49? Well, that's going to be 7. And then what multiplied by itself gets me y to the 4th? Well, y to the 4th is equal to y squared times y squared. So if this is two terms getting multiplied by itself, then it's going to be y squared. I'll separate these out as well just so you can kind of see it. You do not have to do this step though. If you go straight from 64x squared down to 8x, that's okay. I'm just separating it out because I thought that might visually be easier for some people to understand. So I've got the square root of 81 times the square root of x squared times the square root of y to the 6th. What multiplied by itself gets me 81? 9. What multiplied with itself gets me x squared? X. What multiplied with itself gets me y to the 6th? Y to the 3rd. Because if I take just down here to the side, I'll do it down here. If I have y to the 3rd times y to the 3rd, well, we know that when I multiply, I add exponents, so that's going to be y to the 6th. For my last one, I have the square root of 36 times the square root of x squared times the square root of y to the 8th times the square root of z to the 10th. The square root of 36 is 6. The square root of x squared is x. The square root of y to the 8th is y to the 4th. And the square root of z to the 10th is z to the 5th. Now these are all examples of perfect squares. They didn't give us messy numbers. If you get something other than a whole number, it is not going to be a perfect square. So if you get a decimal or a fraction, that is not an example of a perfect square. We're going to look at some examples like that now. So sometimes square roots have expressions that are not easily simplified. In some cases, you have to factor the expression, and hopefully you get a perfect square to simplify. So for example, what if we had something in there like 56? Well, 56 is not on our list of perfect squares. So that's going to make life a little bit more difficult. Or what if we had something like, I don't know, 105? These are examples where we would have to do this next strategy that I'm going to be showing you. So, for example, factor the expression so that you can identify the perfect squares. So here we have 12x to the 3rd is equal to 4 times 3 times x times x times x. So all we did was factor 12 down into 4 times 3, and then we expanded everything out. After that, you evaluate the perfect square and leave the extra factors inside the radicand. So this 4 can be factored into 2, and this pair of x's can be factored into x. Where'd that go? Right here. And then everything else is getting left inside the radical. We're going to break that down and see how that works now. So we'll do it by hand. So we have 45x cubed. What we want to do first is to break this down into its factors. An easy way to do that is to form a factor tree. So I'm just going to write 45 right here, and I'm going to start breaking it down. That's 5 and 9, and then 9 is 3 and 3. So I'm going to rewrite this whole thing underneath the radical, but expanded out with my prime factorization. So I've got 5, 3, and 3, and those are my prime factors. So it's going to be 5 times 3 times 3, and then the x's, I'm going to expand that as well. It's going to be times x times x times x. Now what I'm looking for is I'm looking for pairs. So notice I have a pair of 3's and I have a pair of y's. Now the reason I'm looking for pairs is because remember what it means to square root something. The square root of 16 is 4 times 4. And so that would be the pair of 4's comes to the front. So notice how I always had pairs in this. So now I'm looking kind of like for a pair of socks in these guys. So this pair is going to come to the front. It gets to leave the radical. And this pair is going to come to the front and leave the radical. When they leave the radical, they become 1. So I'm going to have these 3's leave and become 1 unit, so they become a 3. These x's leave and they become 1 unit, so they just become x. So they're taken care of and they're taken care of. Now I need to write whatever is left underneath my radical sign, so that's going to be 5x. And that's my solution. This number and this number are equal. These expressions are the same. They're just written a different way. Let's break down some more things. So we have the square root of 180. I'm going to break that down into its prime factorization. So I'm going to take 180, and I know that that's divisible by 10 and 18. 10 is 2 and 5. 18 is 9 and 2. 9 is 3 and 3. So now I have all my prime factors. I'm going to take those numbers and I'm going to rewrite them underneath the elbow radical. So I'm going to have the square root of, and I'm going to organize it. So I'm going to put my 2's together and my 3's together. So I got 2 times 2 times 3 times 3 times 5. After it's rewritten, I'm going to look for pairs of 2. So I have a pair of 2's here, and I have a pair of 3's here. If I have a pair, they're allowed to come to the front. So this pair's leaving and going to the front, and this pair is leaving and going to the front. So now the 2 goes to the front and the 3 goes to the front, becoming 6, but I'll keep it expanded for right now. So I've got 2 times 3, and so that's taken care of, that's taken care of. What's left over? I've got the square root of 5 left over. Let's multiply that 2 and 3 out because we don't want to make it sloppy, so it's going to be 6 square root 5 for our final answer. Now we have 245x cubed. Let's break down that 245. 245 is divisible by 5, and that gets me 49. 49 is 7 and 7. So let's rewrite this radical, but now I'm going to have it expanded out in my prime factorization. So this is the square root of 5 times 7 times 7 times x times x times x. Now I'm looking for pairs. So I have a pair of 7's and a pair of x's. They're allowed to come to the front because they're pairs. So they're taken care of, and I'm going to write 7x. Now I'm writing anything left over. I had a 5 left over and I had an x left over, so the 5 and the x stay in the radical. We are moving right along. In our next example, I have 8x squared y cubed. Well, 8 is going to break down into 4 and 2 and then 2 and 2. So this is going to be rewritten as 2 times 2 times 2 times x times x times y times y times y. I have one pair of 2's. Now I know that I have this 2 here. It's not allowed to join in. It's not allowed to tag along. This 2 has to have a mate with it before it's allowed to be a pair. I have a pair of x's and I have a pair of y's. So that pair of 2's goes to the front, that pair of x's goes to the front, and that pair of y's goes to the front. So I have 2xy up front. And what do I have left over in my radical? Well, I have this 2 and I have this y, so I have 2y. For example D, I'm breaking down the number 135. So if I break down 135, I'll do it right here. 135 is divisible by 5, and that gets me 27. 27 is 9 and 3, and then that's 3 and 3. So my prime factors, my ends of my factor tree, are 5, 3, 3, and 3. So now let's expand this radical out. So this is going to be 3 times 3 times 3 times 5, and then x times x times x, and then 5 y's. So times y, 2, 3, 4, I'm running out of space, 5. So I have a pair of 3's, I have a pair of x's, and I have 2 pairs of y's. When I pull my 3's out, that becomes 3. When I pull my x's out, they become x. I have a y, and then I have another y. What do I have left over in my radical? I have 3 times 5 times x times y. But we want to make this look neater because this is not very neat yet. So all of this is multiplication. So this is going to be 3xy squared times the square root of 15xy. How did I do that? Well, 3 times 5 is 15. Y times y is y squared. We just have a couple more examples and then we're done with these notes. So now I'm breaking down 192. 192 is divisible by 4, so I'm going to take 192 and 4, and that gets me 48. 48 is divisible by 4 and 12. 12 is divisible by 4 and 3. Now, what you can also do is pull out these pairs of numbers like so, but I will go ahead and bring it all the way down to their prime numbers just so you can see it. So I've got 2, 2, 2, 2, 2, 2, and 3. Let's rewrite that underneath the radical. So I have 2 times 2 times 2 times 2 times 2 times 2 times 3. And I'll check that works. Okay. All right. Now I'm looking for pairs of 2. So I have a pair of 2's, a pair of 2's, and a pair of 2's. So this 4 is coming to the front, this 4 is coming to the, or that 2, sorry, and this 2 is coming to the front. So that's going to be 2 times 2 times 2 times the square root of 3, which will then get us 8. 8 square root 3. Next, I have the square root of 300 y cubed. So if I want to take that 300 and break it down, that can be 10 and 30. And 30 is 6 and 5, which is 2 and 3. And 10 is 2 and 5. So my prime factors are 2, 5, 2, 3, 5. So let's rewrite that underneath the radical. So I have 2 times 2 times 5 times 5 times 3. And then the y's, y cubed is y times y times y. So I'm now looking for pairs, like pairs of socks. So I have a pair of 2's, a pair of 5's, and a pair of y's. Those get to come to the front. So I'm going to have 2 times 5 times y in the front of the radical, and then inside of the radical, I have anything that was not claimed for, so I have a 3 and a y left over. Let's condense this down because this is all multiplication, so this is 10y square root 3y. Just 2 more examples to go. Here I have 32x cubed y squared. 32 is going to break down to 2 and 16. 16 is 4 and 4. That's 2 and 2 and 2 and 2. So we have lots of 2's. So if I were to completely rewrite this, this is going to be 2 times 2 times 2 times 2 times 2, and then my x's times x times x times x, and then times y times y. I ran out of space. Now I'm looking for my pairs. I have a pair of 2's here, I have a pair of 2's here, but this 2 does not have a pair with it, so I can't pull it out. I have a pair of x's, and I have a pair of y's. Let's pull all of those to the front. So this pair is going to the front, this pair is going to the front, this pair, and that pair. So now this pair becomes 2 up front, this pair becomes 2 up front, This pair of x becomes x up top, and this pair of y's becomes a y in the front. Now I need to take care of anything that did not get to move to the front. So these twos are gone, these twos are gone, those x's and those y's. All I have left is a 2 and an x on the inside of my radical. So there we go. And what you should do now is just combine all of this. So 2 times 2 is 4, xy square root 2x. We've just got one more problem and then we're done. What is 75? 75 is 3 and 25. And 25 is 5 and 5. So let's rewrite this. I have 3 times 5, and then 5 x's, 1, 2, 3, 4, 5, and 6 y's, 1, 2, 3, 4, 5, 6. I was able to squeeze them in barely. So I'm looking for pairs. I have a pair of 5's, and then a pair of x's, and another pair of x's. I have a pair of y's, another pair of y's, and another pair of y's. So when I have a pair, I'm able to pull them to the front. So that 5's going to the front, the x is going to the front, another x, a y, another y, and then another y. So I have 5 up front times x up front times x up front times y times y times y. And now I'm asking myself, what do I have left over? Well, it might be hard to find, but we do have a couple things left over. This x right here is left over, and this 3 right here is left over. So the 3 and the x have to stay inside the radical because they didn't have a partner or a pair to go out with. So now I'm just going to condense this all down. This is going to be 5x squared y cubed square root 3x. And there you have it. I hope you have a great night, and we'll be covering more of this in class, so I'll see you soon.